Okay, I think we're going to make a start now. So hello everyone, welcome to this SPF UK Climate Resilience Programme webinar. We've had a bit of a break over the summer, but I'm glad to say we're back with another great seminar today. So my name's Dan Burney. I'm the Science Manager for the UK Climate Resilience team within the Met Office. So I'm going to give you a bit of an overview of some news from the programme from over the summer before we get into the webinar today. Webinar will be about half an hour, and then we'll have lots of time for Q&A at the end of the session. So, typical slide at the beginning here, as those of you who've seen these webinars before. We're going to have the presentation first, and then Q&A at the end and the discussion. If you've got questions that come up as you go along, if you could put them into the Q&A box at any time, then we'll get to those after the presentation. And please do upvote your kind of favourite questions in there, and we'll prioritise those. All attendees are going to remain muted throughout the presentation, or things will just get a bit too chaotic. And the webinar is going to be shared after the event, including the recording, which will be available on YouTube shortly afterwards. If you've got any technical problems at any time, then please put those in the chat and someone should be able to help you with those. And just a reminder of the kind of social media tags that we've got. There's our Twitter feed that you can follow. We've also got lots more information both on the subject of this webinar and all the other projects and programme news on the website. So over the summer, there's been a few more publications have come out from the programme. So the first of these is led by Daniel Koshel at the Met Office, looking at the increase in frequency of extreme daily precipitation events in the UK, particularly focusing on the autumn. That's in weather and climate extremes. And then two papers led by Nigel Arnell. First of these in climate resilience and sustainability on the impact of climate change on policy relevant indicators of temperature in the UK, and another in environmental research communications on indicators of climate risk in the UK at different levels of global warming. So I would advise everyone to have a look at those. And also, there's a new decision support tool. It's available for people to look at on the website. For those of you that were at the last webinar from this series from James Cooper, where it had was talking about erosion hazards and river catchments and their impact on infrastructure, then this project has now produced this new decision tool looking at the case study area around Cockermouth, which I'm sure you remember is repeatedly suffers from quite bad flood events, and this allows you to look at and visualize the impacts of different return period levels of rain events and different durations for different periods in the future. And there's a link to this from the project website and also a direct link at the bottom of the page. I had a bit of a play around with this earlier, and it's well worth having a look. And in wider news, I'm sure it won't have escaped people's attention that COP26 is very soon upon us, and the UK's university network around this as a climate risk summit starting today, and there'll be many UKCR researchers speaking at this, including Ted Shepherd on risks and extremes, Rachel Warren on tipping points, and Charlotte Liddon on communicating impacts. Registration is still open, and there's a link at the bottom of this slide. And also draw your attention to a survey from CEH that's underway at the moment, and this is asking people to kind of assess their interest in river flow projections for future climate and associated data sets. And there's a link here, and anyone who you think would be interested in this kind of data and work, please do send them towards the survey. So before I hand over to Rachel, I just introduce her as Rachel's a marine scientist working within the Met Office, looking at coastal risk and resilience as part of the SPF Climate Resilience Programme. Prior to this, she's got many years experience working in the public and private sector, particularly looking at wave transformation processes and coastal overtopping and coastal flood risk. So I will hand over to Rachel to talk about coastal climate services.
That's great. Thanks very much, Dan. So I'll just share my screen with you and hopefully go into presentation mode. So hopefully everyone can see that. So yeah, I'm going to be talking about the impacts of climate change on the UK coast today. So just quickly to go through the presentation overview. I can't seem to switch between my slides at the minute. Okay, I might just stop sharing and re-share again. Sorry about this. Okay, there we go. Sorry about that. So the overview of the presentation today, we're going to talk about sea level projections and an interactive tool I've been developing over the past couple of years, and then have a discussion around how sea level rise is going to affect coastal risk in the UK. And then hopefully, if we've got time, whether or not we can use global climate models to assess the frequency of weather patterns, again, focusing on the UK. And then at the end, I'm going to sum up with some sort of bullet points on what's next for the project. So sea level projections, why do they matter, and the sea level interactive tool. So I thought I'd start by just giving a bit of an overview into sea level rise. So I've taken these statements from the special report on oceans and cryosphere. So the risk rate related to sea level rise is expected to increase significantly by the end of the century, and it's going to be affecting all low-lying coasts across the globe. And this is in the absence of major adaptation efforts, and there's very high confidence linked to this statement. And then secondly, in the absence of adaptation, we're going to experience more intense and frequent extreme sea level events. And this is expected to increase annual flood damages by 2 to 3 orders of magnitude. Now, sea level rise isn't just going to affect floods, it's also going to affect habitat contraction, geographical shift of associated species, the loss of biodiversity, and increased seawater intrusion into estuaries. And if you're interested in any of those sort of different aspects, then please do go and read the SROC report, because there's a lot of information in there. So as I've mentioned, I've been developing a relocatable sea level tool, and this provides projections of regional sea level based off the climate model simulations from the Coupled Model Intercomparison Project Phase 5, or CMIP 5. And they're based off methods described in the UK CP18 Marine Report or Palmer et al. And there's 2 links on the screen there to those reports that I do recommend you go away and read to understand sort of the baseline science behind all of these. So there are a number of physical processes that contribute to sea level projections, and I've stolen this sort of schematic from IPCC AR5, which I think is really useful to sort of explain all of the different aspects that lead into mean sea level. So at the global level, we're looking at thermal expansion, the melting of glaciers and ice sheets and changes to the land water storage. And then at the regional level, we're looking at the additional effect of local oceanographic processes, including changes in the water density and ocean circulation. Again, we're looking at changes in sort of the land-based ice and water storage. And we've got the additional component of the glacial isostatic adjustment, or GIA. And these all sort of feed into the time mean sea level, which can interact with the tides and the surge to sort of affect the local sea level or extreme events. So how does the tool actually go about sort of deriving these projections? So there's a number of different steps. So the first one here, we're going to loop through the global climate models, so the CMIP models here, and select the nearest grid box for a user-defined site. This produces a map per CMIP model and an associated CSV file with a corresponding metadata. So just to highlight on the map, hopefully you can see we've got a red cross, which is indicating the site that I'm using here as an example. So today I'm looking at North Shields. And then the black dot is just showing the nearest CMIP grid box for each of those different locations. So the tool is set up so that your user-defined site can be based on either a tide gauge name. This will need to be in the permanent service for mean sea levels station list, or you can also use just a simple latitude and longitude location. So once we've selected the nearest grid box to our site from the CMIP models, we use this to calculate the regression slopes between the local oceanographic sea level change and the global thermal expansion component. We do this for two different time periods, 2005 to 2100 and 2050 to 2100. And we do this for all available representative concentration pathways. So in the plots at the bottom here, each point is representative of a year. These are for the 2005 to 2100 sections. And it's just showing the global thermal expansion against the local changes. And then we've also plotted on the one-to-one line. So this is the black dashed line. So a few things to note. The Access 1 model at the far left wasn't run for RCP 2.6. We've only got two sets of data shown on this plot. And then if you look at the HADGEM 2 models, this is the third plot in, you can see that the local sea level is increasing faster than the global average. Whereas in the NOR ESM1 model, we're showing that the local sea level is kind of changing at the same rate as the global average. And these changes are important just to think about going forwards. So then to calculate the total sea level projections for each site that we're looking at, the local thermal expansion component is calculated based on these regression slopes that we've just looked at. But then we also include the additional components of GIA. So for the UK, these are based off estimates that were developed specifically for UK CP18. And elsewhere, these are just based on global GIA estimates. And then we also account for changes to Greenland and Antarctica and all of the other components that we mentioned before. So you'll see in the plot that this step is also reading in the IPCC AR5 projections. This is purely for comparison purposes. So we're comparing the global projections from our interactive tool to IPCC, and you can see that there's a really good match here for North Shields. The bold lines are representing the central estimate, and then the smaller dashed lines or the shaded region is representing our uncertainty range, which is the 5th to the 95th percentile. And then the subplot on the right-hand side is just showing how the local sea level is comparing with the global sea level projections, again for North Shields. So this is for RCP 2.6. And as I skip through, I'm just going to show you the output for RCP 4.5. So you can see here that the scale on the y-axis has just changed slightly as the projections are slightly higher. And then again, RCP 8.5, the scale is increased further again. So we've got a maximum sea level change of around 1.1 meters. And the local projections are kind of more in line with the global projections here. So the final step of our interactive tool is going to read in the sea level projections that we've calculated in step 3, and it uses them for a variety of plotting purposes. So I've got an example at the bottom here, which is showing the regional sea level projections under all 3 scenarios, and then the components of the regional projections under RCP 8.5. So just to note quickly that ocean here represented in the red, that's the thermal expansion component. It's just labelled slightly differently. And it's the only component where we're showing the uncertainty range. This step also reads in the annual mean water level observations from the nearest tide gauge. So our site is North Shields. There is also a tide gauge there, so it's the same location. And this is purely for validation purposes. So you can see the annual mean water level observations from about 1900 then flow seamlessly into the projections of sea level. These observations were also downloaded from the Permanent Service for Mean Sea Level, and they're QA'd before downloading. So you can see here that there are a couple of observations in the early kind of 1970s. They've just been flagged for QA purposes, so it's just something to be aware of. And there should be some metadata on the site to explain why those locations and observations have been flagged. So this slide is just sort of showing some of the additional plots that we can get out of the tool. A lot of this is what we've looked at before, but on the top left here, we're just showing the global and the local sea level change under RCP 8.5. And we've got the different component parts and the uncertainty within this. You can notice here that for Greenland, the uncertainty is significantly more for the global mean than for North Shields itself. Then in the top right, we've got the global and the local projections again and the different component parts, but for each of the different RCP scenarios. Then we've got the local projections in the bottom left again, just illustrated in a slightly different way. And we've also got a plot showing us how uncertainty in the projections is changing with time. So in the earlier part of the century, we're looking at uncertainty predominantly from internal variability, whereas for the latter part of the century, we're looking at more uncertainty from the model or from the different scenarios. So that's a quick introduction into the sea level tool, but I'd like to give you a quick example now of how we've used the tool to respond to some work. So we were contacted by the Ministry of Defence and asked to explore how the risk to coastal locations may change in the future. So for this, we provided sea level projections out to 100 for a variety of UK sites and overseas territories. So this was just a direct output from the tool, just sending off the CSV files. But then we also looked at the implications that these projections have on the extreme water levels for the UK mainland. And for this, we used the coastal flood boundary dataset that was originally developed by the Environment Agency. And there's a link at the bottom of the slide here to the associated report for that dataset. So I've mentioned extreme water levels a few times, but just to sort of refresh us as to what that is, it's the mean sea level and the combined effects this has with the tides and the storm surge. So I've got a very simple schematic on the right-hand side, also from the SROC reports. And this is just showing that the historical centennial extreme sea level, or HCE, which can also be referred to as a 1 in 100 year event, will become much more frequent with sea level rise. So as sea level rise increases the mean sea level, all of the subsequent different return periods above that will also increase. So this is a very simple way of looking at the impacts, and it's actually what we use to respond to the MOD requests. So I've got a couple example statements on the slide of the things I added into the report for them. So providing sea level projections linked to either a 2 or a 3 degree temperature increase, and then giving the mean and the range of those projections as well. And then again, applying this with the coastal flood boundary data set, just to show how much more frequent a different return period water level could be in the future on a variety of different time horizons. So for example, a 1 in 200 year event now might become a 1 in 36 year event by 2050, or even a 1 in 3 year event by 2100. So these estimates have helped inform an assessment for the Defence Estate, and they've contributed to the recently published Ministry of Defence Climate Change and Sustainability Strategic Approach report. And I've got a link there for that report as well, which includes a number of other variables, including like temperature and snowfall. So moving on to the sort of the second part of my presentation, I want to look at how sea level has affected coastal risk within the UK. And to do that, I've used Met Office weather patterns and a tool called Coastal Decider. So I'd like to now just sort of go through what that tool is and what our present day situation is. So these are the Met Office weather patterns. I know they've been presented on before in an SPF webinar, so I'll just do a quick recap on what that is. So they were objectively derived by clustering 154 years worth of emulate mean sea level pressure data. There are 30 patterns. They're ordered based on their annual historic occurrence. The lower numbers occur more in summer, and the higher numbers occur more in winter. And for further details on this, please do go and read Rob's paper that he wrote about sort of how these were set up. The patterns are shown in the diagram on the right-hand side here. And just to pick out two sort of patterns as an example here, we could look at weather pattern 12, which shows high pressure over Scandinavia. And this typically results in a negative skew surge, which is quite important for the work that we're looking at here. Or weather pattern 24, which is showing deep low pressure over the UK and the North Sea. And this results in a positive skew surge. So understanding the variability in these patterns can help us identify sort of unusual patterns that might occur at different times of year. And this can be an indication of severe weather. So for example, weather pattern 30 occurring in the middle of summer. So how do these link to coastal decider? So as mentioned, a subset of these weather patterns are associated with coastal flooding, typically because of storm surges. So Coastal Decider is a tool that's used operationally within the Flood Forecasting Centre, and it's typically a medium to long range forecast product. So it analyses the probability of a heightened risk of coastal flooding around the UK. And these sites are all shown on the map on the right-hand side. So the tide gauge sites are represented as the black crosses, and the wave hindcast sites are represented as the red crosses. And these provide additional sort of information that feeds into the tool, including the daily maximum skew surge and the daily maximum significant wave height or 10-metre wind speed. So what does the tool actually do? What it does is it matches the skew surge value from the historical record, and for this we're using the ERA5 reanalysis product, to one of each of the 30 weather patterns. So for example, on the 1st of December 2000, we might have had a skew surge of around 0.2 metres, and the 1st of December 2000 was also associated with weather pattern 26, for example. So just to note that the Emulate dataset was used to derive the weather patterns originally, but for the analysis purposes here, we're using ERA5 just because of the increased data resolution that this provides. So once we pattern match the skew surges and the weather patterns, we can get a box plot similar to what I've got on the left here. And then we calculate the warning threshold. So this is defined as a 1 in 365 day event, or the 99.7th percentile. So using North Shields as our example again, this would be 0.643 metres, and it's represented as the red dashed line on the plot. So the next step in identifying our coastal risk weather patterns is to calculate the percentage probability of exceeding that warning threshold. So here you can see that weather pattern 13 has only got 0.1% of events exceeding the warning threshold, whereas weather pattern 23 has actually got 1.1% of events. So then the coastal risk weather pattern is defined when this value exceeds a 1% level. So apologies, there's quite a few thresholds in this presentation, but hopefully it all makes sense. So here for North Shields, we can see that our coastal risk weather patterns in the present day are weather pattern 14, 20, 23 and 26. So that then leads me nicely on into the work I've been doing assessing the impacts of sea level change on coastal risk. And I aim to answer two questions. The first one being, what's the increased probability of exceeding the baseline warning threshold? And the second one, just flipping that on its head really, in order to retain the baseline level of risk, what warning threshold do we need? So I've applied sea level projections. I've used the interactive tool that I've sort of explained already. I applied these to 2100 every year, and I've rerun the Coastal Decider approach for a number of different scenarios, a number of percentiles, and a number of time slices. So the table on the right here is just showing the projected sea level anomalies for North Shields relative to the baseline period. And we've got the central estimate in bold and then the uncertainty range in the brackets. So the sea level projections were used to uplift the daily maximum water level. And you can see on the graph on the right-hand side that our axes is now changed to daily maximum uplifted water level minus baseline astronomical tide. So a bit of a mouthful, but you understand roughly what that means now, hopefully. We've left the baseline warning threshold, so the red dashed line has not moved. And you can see that the box and whiskers have all sort of jumped up a bit higher over that line now. So a couple of assumptions for this work before we sort of move on into any sort of more results. The relationship between skew surge and weather pattern does not change. The skew surge height does not change. And the frequency of occurrence of each pattern is the same. And we'll come back to a few of these a bit later in the presentation. So then we go on and we recalculate the percentage probability of exceeding that warning threshold. And I should say that these are the projections for 2050 under RCP 4.5 using the 50th percentile value. So for weather pattern 13, we can see that our percentage probability has increased from 0.1% of events to 1.2% of events. And for weather pattern 23, we've increased from 1.1% of events to approximately 4% of events. So using the same threshold of greater than 1% to define our coastal risk patterns, we can now see that we've got the addition of patterns 13, 21 and 30. So weather patterns 21 and 30 are all both associated with winter conditions. They're cyclonic, they're southwesterlies, and although this will cause a little bit of additional work for people in the Flood Forecasting Centre, they're probably already a risk for another location in the UK, so not too much of a bother. But weather pattern 13 is quite an interesting one. So it's quite evenly spread across the seasons. Typically, it does occur more in the spring and the autumn, and it's associated with anticyclonic northwesterlies. So what we can say here that sea level rise is obviously increasing the current risk or the current patterns, but it's also potentially affecting the seasonality of risk as well. And this could have implications for early warning systems needing to be switched on for a much larger period, or could even have implications for coastal defences as well. But I should mention I've not really looked at seasonality in too much detail, so this is just sort of an early indication. So the next slide here, we've switched from looking at 2050 to 2100, and we've switched from RCP 4.5 to RCP 8.5. And you can see the risk now is really quite stark. So for weather pattern 13, we've got a percentage probability of events exceeding that baseline threshold of 47.95. And for weather pattern 23, we're now up to approximately 61% of events. And you can see that black dashed line of 1% is kind of non-existent on the graph now because all of the weather patterns are showing a risk. So I'll just leave that there for a minute and allow you to sort of absorb the information. But I'll just mention that the risk is not the same everywhere across the country, and the change in the risk is also not the same everywhere across the country. So I've done this analysis for all of the locations that were on the original map for Coastal Decider. And I can say that some places are actually displaying a worse change and have worse risk than North Shields. An example of that would be Newlyn. But also there are other locations that are showing a slightly better result. So an example of that would be, say, Portrush. And this all links back to the spatial differences in sea level rise. And another thing to note here is obviously this is what the risk could be if we don't do anything. So with adaptation measures put in place, this won't actually be the case. So to summarise all of the impacts of sea level rise on the increasing probability, I've tried to just sort of pop it all in a table. So here we've got the weather patterns in column 1 through 30. Then we've got the baseline percentage probability risk. And we've just highlighted those patterns that are exceeding that 1% level. And then the next 3 columns are showing 2050 and the different RCP scenarios. So this is showing a slight increase in the risk with the addition of a couple new weather patterns. And then the final 3 columns are 2100. So that's showing an even larger risk and sort of the inclusion of all the patterns. So to flip it on its head, as I said, one of the other research questions I have was, in order to retain the baseline level of risk, what warning threshold is required? So our baseline threshold for comparison purposes is 0.643. Our baseline coastal risk weather patterns are 14, 20, 23 and 26. So if we want to keep those as our 4 patterns that we're concerned about for North Shields and not include any others, by 2050, under RCP 4.5, the threshold would need to increase to 0.83 metres, which I've got in the table on the left there. And by 2100, this level would need to increase further to around 1.07 metres. So thinking about it this way is quite useful, and when thinking about sort of defence options for communities, whether that's raising a seawall or developing a natural flood management system, or even sort of redesigning homes and raising floor levels. So one of the assumptions I made was that the frequency of weather patterns doesn't change. So this final section of the presentation today is going to explore that in a little bit more detail. So the first thing we need to know is whether or not we can use global climate models to sort of represent the past conditions and future conditions, and then look at whether or not the actual frequency of these weather patterns are changing over time. And I should say that this is work that a colleague of mine, James Pope, has done. So to ensure that the UK CP Global Ensemble members are simulating mean sea level pressure conditions in the present day that are a reasonable reflection of the large-scale circulation, I've performed an assessment against the ERA5 reanalysis product. So the mean sea level pressures in the UK CP Global Ensemble were pattern matched with one of the 30 weather patterns. And this was done in exactly the same way that ERA5 was and the Emulate data was that we spoke about earlier. So UK CP Global is a 15-member Perturbed Parameter Ensemble, or PPE. It was originally run from 1899 to 2099, and the pattern matching has been completed for that entire period. And then what I've done is extract the values from 1979 to 2010 for comparison purposes against ERA5. And a number of fit metrics are available for this pattern matching, but the one that's most relevant for the work that I've been doing is called the pressure anomaly difference, or PAD. So what actually is PAD? The pressure anomaly difference can be defined as the difference measured in hectopascals between a specific ensemble member and its assigned weather pattern. So a positive PAD means that the ensemble member has a higher pressure than the assigned weather pattern, and a negative PAD is just the opposite of this. It has a lower pressure than its assigned weather pattern. And just to note that there are 2 different types of PAD metrics. There's a UK PAD, which is represented as the 9 grid box domain over the UK. And there's also the min PAD, which is calculated using the full sort of grid box that you can see in the map on the right-hand side. So there's a lot more information about this in Rob's paper that I linked to earlier in the presentation. But just in summary, it's sort of just a measure of how well each weather pattern depicts either the forecast or the climate model ensemble. So once we've matched up the UK CP global model, what I've done is created some probability distribution functions of the UK CP global and the ERA5 reanalysis product, and sort of compared the two. So I've overlaid them so that observations here are in blue and the model is in green. So a wider and a shallower PDF is indicating a worse fit between the ensemble member and the weather pattern, whereas if the PAD value is 0, it's kind of a perfect match. And then to determine if these 2 data sets are the same, I've used a Kolmogorov-Smirnov test, or KS test. And this is a great test because it doesn't assume a distribution in the data. And obviously, until we created these graphs, we didn't know. So as with most statistical tests, we have a null hypothesis, which shows that the 2 data sets are the same. And we have an alternate hypothesis, which states that the 2 data samples are different. we get out a test statistic and a p-value. So the test statistic here is showing us the maximum difference between the two CDFs. So this is just a cumulative function of these graphs. So the larger this is, the more likely that the data sets are different. Whereas in our case, as you can see, we've got values of around 0.6, 0.7, 0.06, sorry, and 0.07. So it's highly likely that the two data sets are quite similar. And then the p-value is the statistical significance level. We've set this at around 0.05. So as you can see, these are all greater than that. So we can say statistically significant against the 0.05 level that the observations match with the UKCP global model for Ensemble 1, 5 and 10, as I've got on the screen, and for weather pattern 20. So again, I've got all of the results for all of the ensembles and all of the weather patterns, but that would just be far too much to show today. So we're happy that UKCP global represents the present day. And then we want to see if the fit with the weather patterns is changing over time. So the next thing I did was I redid the assessment, but here we've got the UKCP global historic time slice, so that's 1979 to 2010. And we've got the UKCP global future time slice, so that's 2059 to 2090. So I've performed the same KS test. I've got the same examples on the slide. And you can see, again, the test statistic is still quite small, so values of around 0.08, 0.09. And we've got a p-value. So although this value isn't quite as strong as what we had with our match with observations, it's still greater than the 0.05 significance level. So we're still quite happy that the fit is not changing over time. And therefore, we can use the UKCP global model to look at the changing frequency of weather patterns. So that brings me on quite nicely to my last but one slide. So this is some work, again, I mentioned, done by a colleague of mine, James Pope. And there's quite a lot of information on this graph, so I'll just take a minute to go through it. What we're looking at here is the UKCP PPE ensemble mean of the percentage change in the frequency of occurrence of weather patterns. So we've got weather patterns 1 through 30 along the x-axis, and then we've got our percentage change on the y-axis. You probably can't really see, but the top plot is for meteorological winter. So this is December, January and February. And the bottom plot is for meteorological summer, so June, July and August. And then we've got the results here for RCP 2.6, which is the blue, and RCP 8.5, which is the red. So you can see there's quite a lot of changes in the weather patterns over time. But a useful way that I found to interpret this plot is by thinking of a threshold of change of around plus or minus 20%. So from this, if we look at purely the winter plot, we can see that there are around 9 patterns that are displaying an increase in the summer and a further 10 showing a decrease. But how does this link back to coastal risk? So thinking of we have 7 weather patterns in our present day scenarios that are associated with positive skew surges across the whole of the country now. So not just thinking about North Shields, thinking about everywhere. And 4 of these patterns are actually showing an increase in winter. So we're going to have increased risk in winter months for those patterns. And only 1 of them is actually showing a decrease. So a few conclusions. Sea level is obviously going to pose a significant risk to our coastal communities. And this is actually going to be exacerbated by the changing frequency of these weather patterns, as shown here. So just sort of next steps for the project now. So for the sea level tool that we talked about at the beginning of this presentation, we're shortly planning an internal release within the office of the tool prior to a public release. And the aim is to include some additional science developments here as well, such as using CMIP6 models. The coastal decider, I've sort of shown the results today from the relative importance of sea level and changing frequency of weather patterns. But what we'd like to do is combine the 2 of these together to look at sort of a proxy for coastal risk going forwards. And then another assumption that I mentioned was around some early work that I'm doing now with Nemo surge. So the assumption was that the storm surge shape is not changing with time. So we're looking at whether or not this is an appropriate assumption to have made. And then just one final point from me. I'm working with colleagues across various MPOP organisations to organise a marine workshop for spring 2022 next year. And the hope is that within this workshop, we sort of can connect with stakeholders and maybe find some additional users for this work. And if you're interested in that, then please do email me. My email's on the slide, and I think there's the SBF Climate Resilience website there as well. So thanks very much, and I'll hand back to Dan.
Thanks very much, Rachel. I try and share my screen without losing track of the Q&A. So thanks very much for an excellent presentation there. I think we've got time for about a quarter of an hour of Q&A before a bit of a wrap up. So I'll start taking questions from the Q&A list in, just disappeared from my screen a moment, in order that they've been upvoted during this. So we're going to start with Andrew Coleman's question, which is about if this research is going to be fed into any Environment Agency advice to local authorities on coastal flood risk.
Yeah, great question. Thanks, Andrew. So I should say that quite a lot of our stakeholder engagement has kind of been impacted by COVID, as I'm sure a lot of people's has already. So when we started the work, we had some initial discussions with the Environment Agency about what we were doing and what the plan was. And the hope is in the coming sort of months, like 3 to 6 months, we'll re-engage with the Environment Agency. But as of yet, I can't say really how much the work will feed into anything that they're going to do until we've had those additional discussions.
Okay, and so the next question is about what are the main impacts of a changing climate and increased sea level rise on the MOD estate?
I think what I will, so a lot of the things that we've done for the MOD, we were not allowed to share. So that's why I kind of shared slides that didn't have any locations and that kind of thing in there. So my recommendation is really to go and have a look at their report that they've published. There'll be some great findings in there for sea level rise, but also a variety of other sort of variables as well. We provided information on temperature extremes, on drought, on wildfires. So there's a whole host of sort of climate factors that the MOD are looking at, and they've summarised that and published it in their report. So either, find the link in the presentation that I've given today, or I'm happy to share it with the champions and get it put on the website as well.
Okay, so I think just in addition to that as well, I think it's fair to say we've talked about possibly looking at putting the kind of uplifted coastal flood boundary data into the public domain with these underlying time mean sea level rise assumptions in there as well. So that may well be in the public domain a bit sooner than that. So there's a couple of questions from Suraj and one of Tim Fox's questions, essentially around how does the publication of Working Group 1 from AR6 affect any of the results in here, and is the work that we've done consistent with that?
Yes, I think that's a great question, and I think that sort of links in with the science developments that we're going to aim to include within the sea level tool, so linking with the CMIP6 models or potentially using the SSP scenarios that are in AR6. So that space hasn't really been fleshed out fully. We were waiting for the publication of AR6 before we sort of made our decisions on what we wanted to do going forwards. Around uncertainty, obviously there's a large amount of uncertainty that comes from the Antarctic ice sheets, but this work is sort of focusing more on using the projections that already exist as opposed to sort of creating new projections. So using them for users and making things more sort of easily accessible, I would say.
Great, thanks. And you touched on some other parts of Tim's question there as well about particularly the contributions from West Antarctic ice sheets to sea level rise as well. So there's, again, back to Tim's question and a recent one from Ben Harrison as well about, are there any plans to include some more of the kind of low confidence projections from AR6? So I guess this is around the not being able to rule out the kind of 2 meter levels of global mean sea level rise by 2100.
Yeah, so I guess I've kind of touched on that briefly. I would say that the science developments for the sea level tool are still kind of, everything's kind of on the table. So if there's a use for it going forwards, and that would be important for users, then we'd definitely look into including it. But if there's not really a use for it, then it might be something that we sort of, I don't really want to say gloss over, but focus our attentions in other areas.
Okay, that's great. And so there's a few more questions have come in now. So what's from this is a question from Kate Smith. So what implications do your results have for how we anticipate coastal erosion in the future?
Yeah, that's a great question, actually. And erosion is not something I have looked at in this work, and it's not something I know too much about, other than the fact that it's definitely a key area of research for the Environment Agency in their new strategy. The hope is that some of this work could be used as, I guess, inputs to erosion models or coastal erosion models. So one of those could be, say, like Mike 21, I think it's called. And therefore other users could sort of do a bit of research in that space, how sort of sea level rise is going to affect erosion. So we can provide the sea level information, or we can provide the extreme water level information. But yeah, I haven't really looked at erosion in too much detail, to be honest.
Okay. So I guess, and the final question that we've got in the Q&A chat was, if you're going to be summarising your key findings for Boris Johnson to galvanise national action, how would you do that?
That's a great question. And I've definitely not thought about giving this to Boris Johnson before. I guess to an extent, so we work for the Met Office, so there's a lot of sort of communication from the Met Office to other science departments within government, and there are some sort of key people that work in that area for sort of communicating our science to government. So not just Boris, but the wider sort of department. So I would definitely approach them first, give them my findings, and then work with them quite closely to sort of work it into sort of a report or a kind of a key fact sheet of the main messages of, this is a potential sea level projection, you know, it falls in this range, and this is kind of the impact. So definitely focus on impacts so that we can then get government to focus on adaptation. But yeah, definitely working with the people that have a much better understanding of how government works than how I do.
Okay, and I guess just a final one from Tim. Is the work from this publicly available, and is it going to be published in the peer review literature?
Yeah, so I think you mentioned, Dan, we're looking at publishing something to do with the extreme sea levels in the coming months. So how the sea level projections around the UK interact with that coastal flood boundary data set. That should hopefully be available soon. And then the coastal decider work we're looking to write up in a peer reviewed publication sort of end of the financial year, so sort of spring next year.
Great. So I've had a couple more questions come in. So we've got a few more minutes, so we'll address these. A question from Suraj on when can we expect a public release of this tool? What should users expect from the tool? Well, will there be any customization available?
Yeah, so we're having quite a lot of discussions internally at the Met Office now around this. So the first thing we wanted to focus on was sort of releasing it internally so that we can get as many people within the Met Office using it as possible. And if there are any bugs left in it, because obviously one person can't extensively test a tool of this magnitude, we can iron those out before any public release. I've also been alongside that writing kind of a user guide on sort of how the tool works, and sort of the different things that you'd need to check when you're using it yourself. So that will go alongside the public release. And then I guess the main thing to just think about is how we're going to release it publicly. So it might be that we release it sort of in a research space and release the actual Python-based tool. It might be that we release some of the additional data so that people can sort of have a addition to UKCP, so sort of the extra parts that aren't on the user interface at the minute. So there's quite a lot of discussions going on at the minute as to what we're going to be doing with it. If anyone's got any thoughts, I guess, on what they think would be most useful, then yeah, feel free to send them across and I'll collate them and report back to the team.
Great. And questions come up from Rachel Harcourt, which is really around the kind of exploitation of this. So the question is, how can we use this data to talk to people living in coastal communities? But I take that a bit wider into how we look to actually deliver some impact for different parts and different sectors of the UK and potential stakeholders for this work. Yeah, so the Sea Level tool we've been using quite a lot already. So it's been used for sort of training purposes for the meteorological community in sort of Bangladesh. A couple of colleagues have worked on that. It's also been used to sort of write reports in the Caribbean for sea level projections. And I've used it sort of to respond to a BBC Sport request. So they're sort of the different areas that we've been providing sea level projections for. The BBC Sport was quite a nice one. So it's sort of what the future of sport could look like in the 2050s. And again, it includes quite a lot of different climate change factors. But then I guess to go back to sort of communicating to those sort of coastal communities, I've got quite a lot of experience that I've gained over the years from doing STEM events with school kids and using the tool and sort of providing them projections along with like videos from their local community and what actually happens at the coast during an extreme event is a really useful way, I find, of sort of talking to them and getting them engaged in what they could be doing. Great. So I think we're going to wrap it up there. If there are any questions we haven't got to or any follow-ups occur to anyone, then I think it's fine to get in touch with Rachel afterwards. Yep. So thank you very much for that. So just before we close, just draw your attention to a couple of webinars which are coming up in this series. The first one of these being on the 13th of October. So Andrew Carr and Chris Bishop from DEFRA talking about government approaches to domestic adaptation and resilience. And then on the 17th of November, got Jamie Hannaford from CEH, UK CEH, talking about the eFlag project, which is an enhanced future flows and groundwater climate service to enhance the resilience of the water sector to drought events. And as normal, you can register for the webinar at this link below. So I'd just like to thank Rachel again for an excellent webinar and wish everyone a good rest of their day.